What I'm going to talk about today in this lecture is something called Fischer projections. These seem at first a little bit archaic, but getting the screen in front of us right away, we can see maybe some value here. So Fischer projections are shown by a series of maybe some of these words are familiar to us. That is... Sorry, a little haphazard at the start here. We see down here glucose, and we have galactose. The important thing is these are all sugars, and these types of sugars are simple sugars or simple carbohydrates, but they're all drawn or shown in this very awkward sort of depiction where it looks sort of like a bond line structure, kind of, but the C's are written out, the H's are written out at various places. Maybe you can make out that these are chemical structures, but it's a little bit awkward. What these are just a series of Fischer projections. So this is the Fischer projection depiction of common sugars. Okay, so what I wanted to do with this depiction was to just show you all of these so that you can understand or appreciate why they're so important. Man, sun's in my eyes right now for this lecture. Okay, so we have all of these sugars in front of us drawn in this weird way. What's going on here? So let's get into it. The key thing about Fischer projections are a few things. Number one, the thing to keep in mind is they are weird. That's important to keep in mind because this isn't something that will ever be super intuitive. They're weird, but useful for complicated molecules like sugars. So they're weird. What I mean by that is they're not intuitive, but they allow us to depict stereocenters that are adjacent with some ease. They're probably better than the three-dimensional structure. The issue is that chair structures are, or let me say it this way, sugars exist as chair structures, and we've talked about that. And chair structures make it difficult to assign R and S and visualize the stereocenters. So because we have this sort of perspective, that we have to deal with when we're looking at chair structures, it becomes very difficult to assign R and S and to visualize the stereocenters. So what we do instead was we use a protocol that Emil Fischer developed. And these allow us to quickly, I'm going to put that in quotes. It takes some getting used to. Allow us to quickly determine R and S on acyclic. Let me spell that right. Oh, gotta make that eraser a little easier to manage. Acyclic sugars. And so what we did was we decided, what, sugars exist as rings, but we can also picture them if they're in the absence of water, which is pretty much never. We can picture them in an acyclic or non-ring form. They just have then a bunch of stereocenters that are all in a row. And so what we do is we say, well, let's draw them in this weird sort of chair structure way to show that, to allow us to see how glucose and mannose are different from one another. Okay, so that's me saying why these are important. This is one of those topics that, I'll be honest, um, when I was a student in organic chemistry, I struggled with, and I lost points over and that sort of thing. And then as I got further and further along in my chemistry education and I realized how powerful sugars were, I really regretted missing an opportunity to learn what these were. And I had to basically figure out how to use them later on down the road. The reason why I struggled so much with these is that I I um, I sort of learn them the way that the way that textbooks like to teach them, which is to consider what's called the bow tie structure. Um, so Fischer projections are a way of, I guess, looking at stereocenters in what's called the bow tie arrangement. So Fischer projections look at stereocenters as bow tie structures. I wish I could run, I know I could just turn the page, but I wish I would run out of paper because I don't want to teach you the bow tie structure. I will, it's just not helpful in the grand scheme of things. Okay, now what we're saying with bow tie structures is, let's imagine that we have some tetrahedral carbon and we've got 1, 2, 3, 4 priorities. So the 1 and the 2 are truly over top of each other, but we just twist them askew so that we can see the back and the front. Okay, this is just some tetrahedral carbon. I am then going to rotate it. You could rotate it a number of ways. Maybe you take it this way and this way. I'm just going to rotate it around so that I've got 2 wedges. For every wedge, there must be a dash. What do you mean by 2 wedges? Well, there's the central carbon is now connected, connecting 2 wedges. One goes to priority 1, one goes to priority 2. And then priority 3 is up top. And priority 4 is along the bottom. Now, this isn't a great Fischer projection already because I would really, well, it's fine. It's fine. Okay, anyway. So we have this arrangement. For every wedge, there's a dash. We just happen to have 2 wedges. Well, Willoughby, I really like drawing my tetrahedral centers with 2 straight lines and then 1 wedge and 1 dash. Hey, me too. That's why I taught you that way. It's just easier to kind of deal with. This is what the bow tie structure is. See, it kind of looks like a bow tie. I mean, I know the polo, it doesn't look as good. Okay, but it kind of looks like a bow tie flashing across the side here on the horizontal. Now, what Fischer said was, if we assume that every stereocenter is a bow tie, then let's not draw the wedge and the dash. Let's make life even easier by not only cutting out the carbon atoms, but also cutting out the wedges and dashes, so that we get something like this, where we have 1, 2, 3, 4. Where now the cross, the center of our intersection or cross, I guess I use the word cross a lot more, maybe who knows why, but the intersection of those 2 lines is supposed to be our central C atom that was in the middle of our stereocenter. So the cross or the intersection determines the stereocenter. Okay. So if we go back to our sugars, this is a really nice depiction of our sugars. I'm just going to go backwards to our notes. This is a nice depiction of all of these simple monosaccharides, starting with the simplest of glyceraldehyde, but a more rigorous depiction of the Fischer projection of glyceraldehyde would be, oh, I added an extra CH2, and that eraser is gigantic. Okay. So the most rigorous sort of Fischer projection depiction would be shown in this way for D-glyceraldehyde, where we have our central carbon atom. That is a stereocenter at the intersection. So I think I wrote that in the page, right? The last page of notes that we wrote, but the intersection or the center part of our cross is the stereocenter, and then we draw everything else. We make sure to include hydrogens that are attached to that central stereocenter, but then everything else is just drawn in a typical bond-line arrangement where we omit implicit hydrogens that are not involved in the stereocenter. Okay, so we could do that for all of these sugars, but that's sort of the gist. So I'm going to make note of that. The cross or the intersection determines the stereocenter, and we draw everything attached to the stereocenter. Okay. These things are really useful for drawing molecules where carbon stereocenters are adjacent or right next to each other. So it's really good for depicting adjacent stereocenters. Now, here's the kicker. That's its purpose. Its purpose is to show adjacent stereocenters. But adjacent stereocenters work very poorly with Bowtie structures. But adjacent stereocenters are awful with Bowtie structures. Now, wait a second, Willoughby. Didn't you just say that the Fischer projection is a Bowtie structure, just with lines instead of wedges and dashes? Yeah, hear me out. Okay, so what we want to do is just be able to determine R and S. That's what we ultimately fundamentally have to do, is determine R and S at stereocenters on Fischer projections, or assign R and S at the intersections or the crosses on these Fischer projections. So an important thing to take away from this is to be able to figure out how to determine R and S on Fischer projections. So you need to know how to determine R/S on Fischer projections. That's what you need to be able to do. Now, it's just that it's so rough because we get convoluted and confused by this idea of Bowtie structures and how complicated carbohydrates are. And then why is this even useful? Just give me a bond line structure. I'll figure it out. We've already gotten that far. But again, these things do become useful in various contexts. So just being able to take our skill set from bond line structures and determining R and S there into Fischer projections is very useful and really important. Okay, so how do you do it? So how to do this? I better write a question here. So how? Okay, how? It's really, we just go through the same steps that we do for regular R and S. It's just the number 4 in the back, that aspect of determining R and S has a caveat here. So number 1, prioritize the groups. So 1 through 4. 4 is the lowest priority. Number 1 is the highest priority. Number 2, connect 1 to 2 to 3 if number 4 is in back. Okay, so far it's the same. We have to make sure number 4 is in back, then we connect 1 to 2 to 3. Okay, here's the issue. What does back mean? There are 2 backs. If we had something like this, I don't know. That seems like the Fischer projection that we had before. So what I'm saying is, if we have a Fischer projection where we have 1, 2, 4, and 3, There are two dashes. 3 and 4 are dashes. 3 and 4 are R and back. So do we have to rotate the molecule more? And maybe you can picture it with these wedges and dashes. It certainly took me a few years. But what does it mean for number 4 to be in back? Well, in this case, it means number 4 is not in the back, but on the vertical. So connect 1 to 2 to 3 if number 4 is on the vertical. And I guess the X goes through here, doesn't it? So it's no longer is it in back, it's on the vertical. So what you do is you just treat it like a regular stereo center, and you determine R and S by connecting 1 to 2 to 3 if you assume, or if you see that number 4 is on the vertical. Because if number 4 is on the vertical, it's in back. So that was my big thing that helped me figure out how to work with Fischer projections, is once I recognized that when number 4 is in back, it's also on the vertical. And maybe I should have flipped that sentence. Maybe I should have said, if number 4 is on the vertical, then it's in back. Okay, let's look at an example of that. If I have a situation where I have 1, 2, 3, 4, or if I have a situation where I have 1, 2, 3, 4, in both of these cases, number 4 is in back. So number 4 is on the vertical and is in the back, or a wedge, a dash, for both examples. With that in mind, we just connect 1 to 2 to 3. So I'm going to go 1 to 2 to 3. I do not care about 4. I just ignore 4. So 1 to 2 to 3. Then I'm going to again start from 1 to 2 to 3. I don't care about 4. I don't care where 4 is at. Maybe 4, maybe it makes sense and it goes 1 to 2 to 3, and then 4 just happens to continue on the circle. I just don't care. I do not pay attention to 4, and as long as it's on the vertical. So what I have here is, it looks like in this example I have R, and in this example I have S. Now why is that? Well, the arrow is clockwise on this left example, and the arrow is counterclockwise on the other example. So the cross, or the intersection, defined a stereo center. I'll move over here now, try to stay away from the sun. The cross of the intersection determined a stereo center, and then I just treated that stereo center like anything else. I prioritized the groups. I connected 1 to 2 to 3, made sure 4 was in back. What that means in this case is 4 is on the vertical. And then if it's clockwise, it's R. If it's counterclockwise, it's S. And again, it doesn't matter where 4 is at. If it's on the vertical, I just ignore it as I'm connecting the groups. I could look at another example just so we could see this. Okay, I realized that I could take my green arrow and go 1 to 2 to 3, and it keeps going to 4, but I'm not actually counting 4 as part of this. It's just 1 to 2 to 3. I do not care where 4 is at. And in this case, that would be R again. So that's Fischer projections at the fundamental core. It's really just a different way of looking at stereo centers. And if you want to do some analyses that we're going to do, all you have to do is be able to determine R and S, and you can figure out the answer to any question about Fischer projections, okay? If you can solve for R and S at the individual stereo centers. And the stereo centers are, again, these intersections or these crosses on our structures. So now let's go through some examples, okay? Let's look at the example where we are going to determine R/S for Okay, so this one's not so bad. We look at the elements that are directly attached to our stereocenter. Now, our chiral carbon in this case is just part of the as part of the Fischer projection. It's the cross. So it's always sort of this carbon. I mean, there are some times where people just draw achiral carbons as Fischer projections. It's a waste of time, or it's a professor trying to make sure that you're not falling asleep while you're working on an exam or a problem set or something. But for the most part, nobody would do that. So anyway, we have this. So bromine is the heaviest, then chlorine, excuse me, then oxygen, and the nitrogen. Oh man, number 4 is on the horizontal. So number 4 is on the horizontal. It's not in back. Shoot. What are we going to do? We're going to switch it with something that is in back, or something that is on the vertical. So what do? We switch number 4 with something on the vertical. So what is that? Well, we could go either way, right? We could go either way. We could go up to 3 or down to 2. Let's do both. So I'm going to switch 3 and 4 around. So this is going to be 3 and this is going to be 4. So I've switched those two. And now I'm going to connect from 1 to 2 to 3. If I do that, I get a counterclockwise arrow, which indicates that it's S. But we have to multiply that times -1 to take the opposite of it, which means that our true answer is R. Okay. So our true answer is R for the same reasons that we talked about for regular stereochemistries. I will find a way. I should leave right now and go buy some curtains or something. Okay. Anyway, so we figured out that this stereocenter is R. Alternatively, we could have swapped the other two groups and gotten the same answer. All right. So that was again. And the nice thing is it's a lot faster to draw straight lines than it is to draw wedges and dashes, right? But okay. So we're at 1, 2, 3, 4. And then let me remind myself, I swapped 3 and 4 last time. So I'm going to swap 1 and 2. Excuse me, 4 and 2. So now this becomes 4 down here and 2 over here. So if I connect 1 to 2 to 3, that looks like it's S, but I have to multiply that times -1, which equals R. So it doesn't matter which one we put it on, the top or the bottom, we will get the same answer. Now, this is how you solve these things. You apply the same rules like that we did before, but you've just got a different way of thinking about what's in back. So in back means one of the two vertical positions. And in this case, with one stereocenter, we had a pretty easy time finding which we had an easy time. We could have gone to the top or the bottom. In other cases, it's going to be, you're going to look at the top and be like, ooh, that's the rest of a molecule. Maybe I'll just go down to the bottom as opposed to something really big on top, because I mean, I guess it's just numbers at the end of the day that we're flipping, like a 2 on the top or a 1 on the top, whatever. We're just flipping numbers around and remembering that we did this in our head. But anyway, this is how we solve for R and S. Now, one thing you might suggest to me, which I would appreciate, is, hey, Willoughby, if you take this molecule and I'm going to label this as a weird aspect of Fischer projections. So a weird aspect of Fischer projections, if I take this molecule and I just rotate it 90 degrees clockwise, if I just rotate it 90 degrees clockwise, I'm just going to take it and kind of spin it this way. and I redraw my Fischer projection, I have OH, I have NH2, I have Cl, and I have Br. Then we're going to go 1 to 2, 2, 3 to 4. Hey, when I do this, I don't have to do any switching, right? No, I'm saying no. Even I'm kind of inserting the punchline before I'm done with the joke. Okay, you can't just rotate things 90 degrees in Fischer projection world. Okay, in a bond line structure, I can tumble molecules around. I can make them easier to see what's in front and what's in back. You can't do that for 90-degree rotations on a Fischer projection, and it's the bow tie curse again. So the bow ties coming back to haunt us. If I do this, okay, number 4 is on the vertical, so I just go like this, 1 to 2 to 3, and it looks to be S. That doesn't work. If I do the 90-degree rotation, I get S. And I don't know if I should flip it or not. Okay? Well, the true answer to this molecule is that it indeed has an R configuration, or it has an R assignment. So R is the correct answer. And we got that from our swap rule. If we do a 90-degree rotation, what I have to recognize is that these are different molecules. So a weird aspect of Fischer projections is that if you rotate them 90 degrees, you get to a different molecule. You've flipped the stereocenter, it turns out. So rotating a Fischer projection 90 degrees will flip stereocenters. What I did by rotating it 90 degrees was I did the equivalent of taking a stereocenter in a bond line format and switching the stereocenter from having a wedge to a bromine to a dash to a bromine, or a wedge to a hydrogen to a dash to a hydrogen. Okay, so it would be like me saying, okay, if you see a stereocenter and hydrogen is drawn as a wedge, just draw it as a dash. Who cares? Don't worry about rotating it around. Well, come on. If you do that, you're not really putting it in back. You're actually breaking bonds. You're pulling the hydrogen off. You're pulling off the substituent that was in back, switching them, rebonding them. That's that's chemistry. That's new molecules. That's not rotating it around correctly in space. Similarly, because of the bow tie nature of Fischer projections, we can't just rotate things 90 degrees. It's actually the same as breaking bonds and making bonds. You really have to be careful about rotating Fischer projections around. Rotating them 90 degrees or 270 degrees will flip stereocenters, but rotating 180 or 360 degrees keeps everything the same. Honestly, I hate to be colloquial, it was all this crap that really threw me with Fischer projections. Like, once you feel like you can visualize a bow tie structure and determine RNS from bow tie structure, and then you go through that hurdle, and it is a hurdle. It's harder to rotate bow ties than it is to rotate a normally drawn tetrahedral center. But once you get that far, and then you hear things like, yeah, if you rotate it 90 degrees, some weird stuff happens. You start doing chemistry. At that point, in the midst of Organic 1, it was like past midterms. I was getting stressed out. It's a busy semester. At that point, it's like, I don't understand why this is important. This is important. Show me some molecules. Well, if I had just told myself back then, just know how to assign RNS and you can figure all of it out, then I'd be like, oh, okay, that's really helpful. So just knowing how to assign RNS at the stereocenters is going to allow you to be able to use Fischer projections productively. The goal is not to be able to visualize the Fischer projection to a bow tie structure, to a bond line structure. That's not the goal. The goal is to assign RNS on a Fischer projection, assign RNS in a bond line structure, and then compare the two. Okay, let's look at it this way. What you need to be able to do, be able to compare bond line and Fischer projections to show if they're the same, or to know if they're the same. Or if they're different from each other. So we want to be able to know if they're the same or if they're different from each other. Okay, so let's look at let's do, yeah, this is fine. It's not a very stable molecule. Let's do this molecule. Okay. So let's see, I just pulled this one out of my hat. So we have a star, we have one stereocenter with an OH and an NH2. I don't want you to even think about picturing a bow tie structure. I just want you to kind of, let's think through this and try to figure out if we can predict what this would look like as a bond line structure. Well, there's a carbon chain in here, right? 1, 2, 3, 4. There's a carbon chain. And then at one carbon, there's an OH and an NH2. Okay, an OH and an NH2. Now again, I just pulled this out of my hat. I don't know whether that's a wedge or a dash on the OH or the NH2. Well, let's see. Let's, I don't know, let's take a guess. Let's guess that the OH is a wedge and the NH2 is a dash. Oh, let's just see what happens. Okay, well, what we should do is we should determine RNS. So we know this is a stereocenter. It actually, the stereocenter has the same connectivity as the Fischer projection. We have an ethyl group. We have an ethyl group on the Fischer projection on the bond line structure. We have a methyl group, the Fischer projection on the bond line structure, both coming out of carbon star. We've got an OH. And we've got an NH2. Hopefully those colors are different enough from you. I'm trusting that they're different. Okay, so we have a stereocenter with the same connectivity, but is the orientation the same between those two? Are these two structures the same, or do they happen to be, do we happen to have accidentally flipped all of the stereocenters or have drawn enantiomers of each other? Well, let's assign RNS at both and see what happens. Since the connectivity is the same, if the RS assignment on both of them is the same, it's the same molecule. If the RS assignment is the opposite or different in both of these, because there's a single stereocenter, we know then that they would be enantiomers of each other in different molecules. So did we do a good job? We just took our original molecule as a Fischer projection, drew a bond line structure with the appropriate connectivity, took a guess without picturing anything with a bow tie structure to see if they're the same. Maybe some of you, I mean, I'm not going down the road of a bow tie structure. I don't think I ever want to draw one again in these lectures. Okay, so let's go ahead without further ado. So 1 goes to the oxygen, and I'll circle my priorities. 2 goes to the nitrogen, 3 goes to the ethyl group, and 4 goes to the methyl group. Okay. So we could, while that's fresh in our head, 4 on methyl, 3 on ethyl, 1 on OH, 2 on NH2. Ooh, man, I've got molecules where number 2 is in the back on the in the bond line structure, and number 4 is on the horizontal. I've broken all the rules. That's okay. I just have to do some switching, right? I just have to do some switching. So I'm going to switch 4 with 2 in this case. So I'm going to put 2 right here and 4 then down here. That allows me to then connect from 1 to 2 to 3. I'm ignoring 4 altogether, right? I always ignore 4. It doesn't matter if it's a Fischer projection or a bond line structure. Now I'm going to do the exact same thing over here. So with bond line structures, we replace 4 with whatever is in the back. So then 2 goes right here and 4 goes right here. So now I go 1 to 2 to 3. As I look, did I do this right? I have S and I have R, times -1. Right? Because it's clockwise arrow. So if it's a clockwise arrow, it's R, but because we did the switch, we have to go back to S. You guys seeing what I'm seeing? If we go over to our other one, S times -1 is equal to R. I have to flip it, right? I can't just say it's S because I had to flip the groups to get in back. I was just hyping up how great this is. What are we going to do? We tried to convert the Fischer projection into a bond line structure. We got the connectivity right, but we didn't get the stereochemistry right. Does that mean we have to start all over? No, it's not even a big deal. It's not even a big deal. We took a guess. It took like 2 seconds to draw this structure, right? It took like 2 seconds. Once we made sure we had the connectivity, and maybe it was a little bit slower for you, but you'll get there, okay? It took not very much time to draw that. And then we were like, wait, there's got to be a wedge and a dash somewhere. Let's just throw some on. For every wedge, there's a dash. Let's put 2 straight lines to make life easier. Okay, so we have 2 straight lines, a wedge and a dash. We got it wrong. Who cares? Flip something around. What I'm saying is that our original guess was wrong. That's no big deal because all we have to do is draw another bond line structure and let's flip something around. Let's make the NH2 a wedge and then have the OH a dash. If I do that, I flip it from S to R, or excuse me, from R to S. All right, let's prove that to ourselves. So we've already done the priority. So it goes 1 to 2 to 3 to 4. I know what you're thinking, Willoughby, why don't you just set yourself up so you didn't have to do this little flip? But that's okay. 1 and then 4. And then we go from 1 to 2 to 3. So now it looks like R, but we have to multiply that by -1, which equals S. Now they're the same. That's pretty cool. You know why that's cool? Because we took a Fischer projection with this super awkward, I'm just going to say it, super stupid bow tie arrangement. But we converted it into a bond line structure just by doing like a little guess and check. We guessed a structure. We made sure it had the same connectivity. And if you have the same connectivity and the same RS assignment, it's the same molecule, just depicted differently. So they're the same molecule. Same connectivity, same RS assignment, equals the same structure. We're going to take advantage of this. This is my 8th time teaching this class. And what I found is that no matter how much we all want them to go away, Fischer projections aren't going anywhere. They're so important for understanding carbohydrate chemistry, and they're ingrained deep into biochemistry. That makes them important. That makes them something that we have to learn. Now, I say they're troublesome and I make fun of them because it's the bow tie structure makes them so weird. It's hard for me to visualize, and I've been thinking about visualizing molecules since like, I don't know, 2005 or something, so 15 years. I've been visualizing molecules and rolling them around in my head, spinning them on their axes and all that sort of thing. But going from a bow tie structure to just a conventional bond line structure is still really difficult for me. It wasn't until I realized that if I can determine R and S on the bond line structure and the Fischer projection, which for the most part take on the same rules, there's this vertical horizontal thing with Fischer projections. But if I can do that with both of them and just compare the two and show that I can then know if two molecules are the same, if one's depicted as a Fischer projection, one's a bond line structure. So that then allows me, if I can know they're the same, then just by guessing and checking, I can convert from a Fischer projection to a bond line structure and back and forth. Okay, I just make sure the connectivity is the same. I make sure the RNS assignment's the same, and boom, they're the same molecules, and we can do something that 90% of the other organic chemistry students in the world cannot do. Okay. In the next lecture, we'll practice this more. We'll look at some specific examples and we'll move between Fischer projections and bond line structures.